Our today's topic of the first session is about multinomial distribution and multivariate distribution. So first of all, we'll try to understand what is the basic difference between these two distributions. Let us first talk about multinomial distributions and try to identify the parameters of such distributions. Also, I will show you one or two problems with respect to multinomial case. Now, so far we have studied binomial distribution, and you know that binomial distribution is a kind of discrete probability distribution where three conditions are to be satisfied. One condition is that when you repeat the experiment, for each of these experiments being repeated must be associated with two outcomes only. One outcome is called success and another outcome is called failure. And if you know the probabilities of such outcome, then that outcome's probability must remain same from experiment to experiment. So probability of success, if there is any, if by there is any, I mean to say that if you can find it, then that probability of success remains same even if you repeat the experiment for some time. Because you know, as we allot the probabilities to the events, and that can only be done under the condition that the system is unbiased. So that's why I have said that if you know that probability exists, that the system is unbiased, then probability of success is known, and in that case, you can check whether it remains same throughout the experiments you perform. And each time you perform the experiment and the outcome you obtain, these outcomes of the subsequent experiments will not be dependent upon what outcome you have got in the previous experiments. So in other words, the trials must be independent. On the other hand, if there are n independent trials permitting two outcomes, two possible outcomes, one is success and another is failure, such that if we write the probability of success to be small p and to a probability of failure to be small q, such that p plus q equals to 1, and the associated random variable is only one, that is capital X, then such a distribution is called binomial distribution if it has the probability mass function of the following form, that ncx p to the power x q to the power n minus x, where possible number of appearance of the outcomes will range from 0, 1, 2 up to the total number of experiments. But on the other hand, suppose we are repeating a trial for n times, and suppose in such case k mutually exclusive outcomes appear. In binomial case, we had only two outcomes possible. Now I'm generalizing the fact to k outcomes. Then if this happen, and if each of these k outcomes are having probabilities, respective probabilities as θ1, θ2, θk, so that the total probability is 1. And if in the experiment we consider, instead of having one random variable will be considered definitely, that is the mother random variable, but that random variable will have different types of subset of random variables, which we denote by capital X1, capital X2, capital Xn, according to the situation under consideration. Then actually we'll have to be interested on not pairs of random variables, but n tuples of random variables. Okay, so suppose instead of getting capital x as only one random variable, if we get two random variables at some point, capital X and capital Y, for single random variable, we study its probability distribution, unique probability distribution that it follows. But if there are two random variables, we have to study not two random don't think that for two random variables we have to study two different probability distributions, but on the other hand we study their joint probability distribution, so we have to consider their joint sample space. Okay, and in that scenario we can consider several different random variables like x1 x2 dot 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 xn, okay, where whose joint probability mass function will be considered. Now try to see at the two, in these two situations, where in one situation I'm talking about, I'm not talking about the random variables, I'm talking about the number of outcomes, where the number of outcomes is not restricted to two only, it is actually more than two. And in another case, we are talking about the number of variables whose joint probability mass function is being considered. So these two scenarios are actually different. That has been mentioned as small a and small b. And the small a, in the small a case, the mother variable is capital X. And after repetition of the experiment, we have small k mutually outcomes, mutually exclusive outcomes. This is the case of multinomial distribution, which is depicted in the part A, and where we are considering n tuples of random variables having some joint probability mass function or joint probability distribution. This is the case of multivariate distribution. So this is the difference between multinomial distribution and multivariate distribution. I can see that there are 50 participants, but only 30 participants have so far written their roll numbers in the chat box. Other, if you miss, then you will miss the class. Now, to start with, let us first discuss about the multinomial, the definition of multinomial distribution. To define multinomial distribution, we have considered small n random variables, capital X1, capital X2, capital Xn. But do not think that since you have considered more than n random, more than one random variable, it is a multivariate case I am discussing. Capital X is the mother variable. At some point of time, capital X1 is the subset of capital X. At some other point, capital X2 is the subset of capital X, and so on. In this manner, capital X1 is can be considered to be the part of capital X at some point, having certain value as small x1. Capital X2 is the part of capital X at some point, having certain value x2, and so on. So if we consider such random variables x1, x2, dot 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 xn, such a random variable will have multinomial distribution, and they are referred to as multinomial random variables if and only if their joint probability distribution is given by f of x1, x2, dot 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 xk, small n is there, theta 1, theta 2, dot 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 theta k. These are the probabilities of this, or each of these outcomes. And this probability function can be written as by this notation, where I have written, it looks like NCX, but we shall not call it as NCX. This is a notation which stands for n factorial by x1 factorial, x2 factorial multiplied by xk factorial. So this bracket which have been used over here, don't make yourself confused that this bracket is NCX. This is just a notation which has been used for this factor, multiplied by this probability raised to the power x1, this probability raised to the power x2, this probability raised to the power xk, where for each I, this xi can take any value 0, 1 to up to n. Okay, So x1 can take values ranging from 0 to n. X2 can take value ranging from 0 to n. Xk can take values ranging from 0 to n. So if this happens, and if we can check that this total of these number of random variables, these values x1, x2, xk, gives you the total number of experiment, that is n. And corresponding to that, if we consider all these probabilities together and add them up, if it sum to 1, if these two conditions are satisfied and their joint probability distribution is of the form this, then such a variable, such a n tuple of variables is called to have a kind of multinomial distribution. You can, at this point, you can ask me one question, that it looks very similar that the case is a multivariate case. The answer is yes. The definition has been set in such a way so that together they have considered the multivariate and multinomial case. Multivariate case has been considered because these different random variables have been considered, and multinomial case is being considered over here because of this form of the probability function, where x1, x2, xk, these are the successes, mutually exclusive successes, which appear with certain probabilities in this scenario. So let us try to solve a particular problem which is given in problem 1. Problem 1 says that according to the Mendelian theory of heredity, if plants with round yellow seeds are crossbred with plants with wrinkled green seeds, the probabilities of getting a plant that produces round yellow seeds, wrinkled yellow seeds, round green seeds, or wrinkled green seeds are respectively given by 9 by 16, 3 by 16, 3 by 16, and 1 by 16. Question is, what is the probability that among 9 plants thus obtained, there will be 4 that produce round yellow seeds, 2 that produce wrinkled yellow seeds, 3 that produce round green seeds, and none that produce wrinkled green seeds. Now this question, when we encounter such a question, we try to find out whether it is having properties of any of the known probability distribution. Just now we have learned about multinomial case. Let us try to find out whether this particular problem satisfies all the characteristics of the multinomial case, and if it is so, then we will try to solve this problem. You will only help me to calculate the expression which I'll be obtaining after applying the probability mass function of the multinomial case, because that is the part that you are going to play with. And when I'll ask you to calculate the figure, you will calculate the figure and you will write in the chat box. That will be helpful for me. Now this example, that Mendelian theory of heredity, this example is very important in the sense that it comes directly from the biogenetics. And you can say that this kind of study was actually the the basis on which the theory of genes have been developed, and consequently the theory of cancers. So this study, from that perspective, this type of study is very important. Okay, let us not discuss the premise of the problem. You try to think of the premise. Let us try to find out whether it satisfies the parameters of the multinomial case or not. To begin with, we first identify that what are the things that we are interested about in this particular case. So you see that round yellow seeds have been crossbred with plants with wrinkled green seeds. Okay. And after this crossbred, what have we obtained? What different cases have we obtained? Let us try to figure it out. One case that has been obtained is round yellow seeds that can appear. Okay. Another case that has been obtained is wrinkled yellow seeds. Another case that appear is round green seeds. And the last one is wrinkled green seeds. We can associate mother variables to these different cases. So let us associate the mother variables to be capital X1 for this, capital X2 for this, capital X3 for this, and capital X4 for this. Now what else is given? These things, after this crossbreeding, these cases are appearing with some probabilities which are given over here. So let us try to note down the probabilities as it is given. So round yellow green seeds is having the probability 9/16. Wrinkled yellow seeds is having the probability 3/16. Round green seeds is having the probability 3/16. And wrinkled green seeds is having the probability 1/16. If I compare this particular problem with the given conditions of the multinomial distribution, you can say that this is your theta1, this is your theta2, this is your theta3, and this is your theta4. And what we see is that if we add all these thetas, we get 9 plus 3, that is 12, plus 3, that is 15, plus 1, that is 16, which is 1. So one condition is being satisfied. What else is given with respect to this problem? It is given that we are supposed to find the probability that there will be 4 that produce round yellow seeds. So some number, some value is associated with that. It is called, we may call it as X1, which is 4. 2 that produce wrinkled yellow seeds. So one value is being associated with that. We call it X2, which is having value 2. 3 that produce round green seeds. It is X3, that is, which is called 3. And X4 is the variable which is associated with the wrinkled green seeds having no value. And if I add these variables together, what we find? We find 4 plus 2, that is 6, plus 3, that is 9, plus 0, that is 9, which is equal to 9. And here you see that we are going to study 9 plants, which is equal to your n. So the second condition is also being satisfied. This study implies that all the parameters which are essential for studying multinomial case are known to me. And so we are in a position to apply the joint probability of multinomial distribution. So the probability that 2, or you can, if you want to stick to the notation given in the definition, which is written as small f, not capital P. So we are to find here small fx is the probability. Remember, fx1 dot 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 this xn, this is the probability I'm talking about. So we want to find the probability that there will be 4 round yellow seeds, 2 wrinkled yellow seeds, 3 green yellow seeds, 0 wrinkled green seeds, put a semicolon. You are studying 9 seeds. The probabilities respectively are given to be 9 by 16, 3 by 16, 3 by 16, 1 by 16. So if I write like this, we get 9 factorial by 4 factorial, 2 factorial, 3 factorial, 0 factorial, and 4 to the power, sorry, not 4 to the power, theta 1 to the power x1. So this would be 9 by 16 to the power 4, 3 by 16 to the power 2, 3 by 16 to the power 3, and 1 by 16 to the power 0. So we can apply this probability over here and we can calculate it. Now I'm asking all of you, take your scientific calculator and try to find out this particular value. Once you get it, write in the chat box. So I'm waiting for your reply. A very big expression. Only scientific calculator can help you in this particular matter. So I was asking you to calculate this. Otherwise, if you are not able to do so, then I have to do it by myself, I think. But in that scenario, I shall not be able to verify whether my calculation is right or wrong. That can only be verified if somebody else does it simultaneously. I'm also trying to calculate. Okay, I have obtained one value. Okay, let's see what you have written. Yeah, now I can see that Sohini has written 0.02923. Others have written, Shovik, Shomili, they have written 0.029. I shall stick to this 0.02923. As many points as you keep after the decimal, that is much more better in the case of calculation of probabilities and proportions. Okay, you can round up things, but anyways, everybody has got a correct answer. I mean, same answer. My answer is also matching with you. So that means you see that the thing can be easily done by applying the multinomial probability distribution in this scenario. Okay. So let me erase these things. Otherwise, there will be trouble. I hope that you have all written the things properly in your copy. Now, let's try to find out what further things we have in our note. Okay. Yeah, there is another problem, problem number 2, which I'll try to quickly do. It's also a multinomial case, I think. That's why I have written the problem over here. And the problem says, let's see what it says. If 18 defective glass bricks include 10 that have cracks but no discoloration, 5 that have discoloration but no cracks, 3 that have cracks and discoloration, what is the probability that among 6 of the bricks chosen at random for further checks, 3 will have cracks but no discoloration, 1 will have discoloration but no cracks, and 2 will have cracks and no discoloration. First of all, we will try to note down what are the different cases that are arising in the current scenario. The first case that is arising, case 1, is cracks but no discoloration. That is one case which we are getting. Case 2, discoloration but no cracks. Okay, that is another case we are getting. And case 3 is both cracks and discoloration. Okay, so these are the 3 cases which we have got, and associated to that we can associate random variables to them. And you see that carefully observe that this statement is given among 6 of the bricks. So that means you are studying 6 items. That becomes your small n. You are studying 6 items, that becomes your small n. And you are trying to check whether this, when you actually repeat this experiment, to which category of cases your outcome falls. Now you have observed that x1 equal to 3, because 3 will have cracks but no discoloration. You have observed that x2 is equal to 1, because 1 will have discoloration but no cracks, and you have observed 2 will have cracks and discoloration, so x3 will be 2. And also it is written in the beginning of the problem that if 18 defective glass bricks, if 18 glass bricks were there, and they include 10 that have cracks but no discoloration, 5 that have no that have cracks but no discoloration, 5 that have discoloration but no cracks, and 3 that have cracks and discoloration, and nothing is mentioned here whether the situation is biased or not. So we can definitely assume that the situation to be unbiased, and we can, with the help of classical definition of probability, we can allocate the probabilities. So from the above sentence, we can very well put the probability θ1, we can associate the probability θ1 to the case 1 as 10 by 18. We can associate the probability θ2 to x2 as 5 by 18. And we can associate the probability θ3 with to x3 as 3 by 18. And you can check that if I add these 3 figures, 10 plus 5 give you 15 plus 3, that is 18, which is 1. 18 by 18 is 1. And if I add these 3 plus 2 plus 1 gives you 6, which is equal to n. So summation I goes from 1 to 3 xi is equal to n, which is 6. And summation I goes from 1 to 3 theta I is equal to 1. All the conditions are satisfied, and therefore you want to find 3, 1, 2 with 6 times the experiment is repeated. Respective probabilities are 10 by 18, 5 by 18, 3 by 18. And if I do so, the probability comes out to be 6 factorial by 3 factorial, 1 factorial, 2 factorial multiplied by 10 by 18 to the power 3, 5 by 18 to the power 1, 3 by 18 to the power 2. Please help me to find out what value comes out of it, just as before. I'm waiting for your reply. Now someone has written, okay, 0.07938. Anjali has got 0.07938. Rohini has got 0.07938. So this is 0.07938 approximately. So see, this problem can also be done. What is the difference between the earlier one and the previous one? In the earlier one, probabilities were directly given. In this case, the probabilities have been calculated under the condition that the situation is unbiased. So I'm going to erase the things over here. A cautionary statement regarding the problem number 2 is that both the problem number 1 and problem number 2 has been selected from the exercise of John Freund book. You can find it very well. You can now, even if you can now see, try to look for these problems. I cannot recall the page numbers. Okay, you just go through the PDF and you'll find that in the exercise, both the two problems are there. But so far as I can remember, problem number 2's answer is misprinted. Instead of writing 0.079, it is written 0.097. So you have to rectify it you have to note it down. Okay, so that answer is misprinted. So take care. So because sometimes later, if you try to do the calculation once again, and if you go through the exercises, you can someday you may WhatsApp me that, sir, this answer is not matching, some different answer is given. So that doubt, I'm actually trying to clarify this doubt. The answer to problem number 1 has been actually these answers are matching. That is given in the Excel solution. I mean the answer which is mentioned in the printed in the solution, that are matching. And you know, in these types of books, only odd numbered questions are answered. So I deliberately tried to pick up these two problems so that I can match the answers. Okay. So I found the observation which I have found. I'm sharing that observation with you. And the third problem I'm not going to discuss because it is also a kind of multinomial case. But this problem you can find that it is solved in the book itself. So that problem I actually copied over here. Okay, so similar to the previous ones, I'm not going to discuss it anymore. You can understand. Next comes a special case of multivariate distribution, which is called a bivariate distribution. Okay, not always the probability distribution looks like the way it is given above, like that form which we have theta1 to the power x1 plus theta2 to the power x2, like this, multiplied by some numerical factor. Not always this is the case. Just like we try to find out what is the probability distribution of a binomial, what if a random variable is there, a situation is there, what is the probability distribution can be for such cases. Here we'll try to find out if two random variables are there, how to find their joint probability distribution by considering the following case. First of all, we have to understand what is bivariate distribution. As the name suggests, this bi stands for the word two. So variate is a statistic word which is very famous in the domain of statistics. Variate is actually means variable. So bivariate means two variable. A distribution having two variables is called bivariate distribution. And obviously it is a special case of multivariate distribution. How we can define this bivariate distribution? If capital X and capital Y are discrete random variables. So obviously, in the univariate case, that means single variable case, we started with discrete problems. Here also, we'll first start with the discrete problems. Then gradually we'll move on to the continuous case. So if capital X and capital Y are discrete random variables, we write the probability that capital X will take on the value small x and capital Y will take on the value small y, as this is the way by which it is written, by putting a comma in between. because we are considering the two things simultaneously. So we put a comma in between. We write probability that capital X is taking the value small x, and at the same time, capital Y is taking the value small y. This is denoted by this notation. And thus, this probability is the probability of the intersection of the events capital X equal to small x and capital Y equal to small y. As in the univariate case, where we dealt with one random variable and could display the probabilities associated with all values of x by means of a table, we can now in the bivariate case display the probabilities associated with all pairs of values of capital X and Y by means of a table. These tables are actually studied because if we can write the sample space, if you can write the probabilities, at least we will try to find out, is there any formula which can justify these probabilities? This probability mass function in binomial distributions case, in probability mass function in Poiseuille's distribution case, these are all a kind of formula, you see. So before those formulas were arrived at, the mathematicians Poiseuille, Bernoulli, they actually studied the system, noted down all the possible outcomes of the system, and their respective probabilities were found. And then they try to they set to think whether they can they can introduce any formula which will justify the binomial case, which can justify the Poiseuille case, and so on. So here also, if two variables are given to me, a situation is given to me, we'll try to design a table with the values of the random variables and their respective probabilities. And after that, we'll try to find whether these probabilities can be regenerated with the help of any particular formula or not. And if it is so, then that formula will be termed as the probability mass function of the current binomial of the situation, bivariate situation, which is in our hand. We are going to discuss the problem in the next session. Okay, I'm going to stop the recording for now.